here's cleanup or finishing up of, I think this is section 1.1. And what's left in here is so at the end, okay, at the end of 1.1, the authors, they introduce the notation z equal x plus iy equal xy. Okay, so we can use either of these notations, and typically we'll use the x plus iy, I think, for a lot of what we do. But they point out that the I is definitely there. So if you think about what I would be, that would be, if I wanted to just write I, I would, and maybe here instead of an equals, I should put 3 lines like defined as. So I could do this, 0, 1, and now notice, if I do I squared, okay, so I squared then would be my 0, 1 times 0, 1, and then by my definition, right, that would be 0 times 0 minus 1 times 1, and then 0 times 1 plus 0 times 1. And so you see we get minus 1 and 0. And so there is that idea of I squared being negative 1, even in this other notation, this Cartesian coordinate notation. Not sure, I'm kind of playing with this stuff here because getting bigger and smaller. So sorry if I'm making you dizzy. Okay, so there's that idea of I squared and negative 1. Again, it works in the ordered pair notation. And then for further cleanup, they mention the fundamental theorem of algebra. And we need a lot of work to prove this. And so I guess they're just doing this to kind of say, hey, here's a great reason to study complex variables. And that is that every non-constant polynomial of degree d has d roots And then they point out this is counting multiplicity. In the complex number C. And so that is a big deal. We can factor every polynomial down to all its, all roots. So, it used to be if we had something like z squared plus 1, we would say, oh, we couldn't factor that. But now we can, you see, we can factor this into z plus I, z minus I. Okay, and I certainly could have put an x there, but since I knew the answer was going to be a complex number anyway, the I and minus I, I just went ahead and used z. So for our polynomials, we can always just put a z there, assuming that some of the roots may be complex numbers. But so again, to check this, multiplying this out, right, I get z squared, then plus zi minus zi, and then minus I squared. Okay, but that's z squared. Those make 0. And then I've got minus I squared, but I squared is -1. And so this is z squared plus 1. So where we used to not be able to factor that, now we can. So it used to be our factor theorem in real numbers is that I can factor any polynomial into either linear terms or non-reducible quadratics. So this would be in real numbers, this z squared plus 1 here would be what I'd call an irreducible quadratic because I can't factor it within the real numbers. But I can factor it within the complex numbers. And so all these quadratics I can now factor that I didn't used to be able to. Okay, and that finishes up section 1.1.